This is lecture 31, and today we will be talking about calorimetry. What is calorimetry? Specifically, calorimetry is the measuring of calories. What are we talking about when we're talking about calories? We're talking about the quantity of energy transferred during a physical process or chemical reaction. So in our last lecture, we ended with this problem, where we took a 20-gram piece of iron, we heated it to 1000 degrees Celsius and then dropped it into 1 liter of water at 25 degrees Celsius and wanted to figure out the final temperature of the water and iron. And I said this is how we actually do heat capacity measurements, and it is. So we'll review this problem really fast, and then we'll go on to more formal discussion of heat capacity. So the thing we have to recognize, though, in this problem and in all of our calorimetry problems is that the final temperature of everything is going to be the same. Everything is going to reach equilibrium in the end. And what that means is that we're going to lose some heat from iron, and it's going to equilibrate with the water. And so all the heat that's lost from the iron is going to be gained by our water here. So we came up with this expression that the negative Q of our iron is going to be equal to the positive Q of our water, right? Iron is losing heat, water is gaining it. And from that, we can then come up with these two equations where heat, when we're heating or cooling an object, is just equal to mc delta T, where of course every object has its own mass, its own C, and its own delta T. We then realized that we can plug in our initial temperatures here because delta T is just going to be T final minus T initial, and that each of the iron and water are going to have different initial temperatures, but they'll all have the same final temperature. And then from here, we just do some algebra, we rearrange some things, and finally solve for our final temperature to figure out how much this has changed the temperature of our water. Let's give you a chance, though, to try this out. Let's say we've got 1 kilogram of hot iron. It's got a heat capacity listed here. And the hot iron is 200 degrees Celsius, and it's dropped into a bath of water. And the water has a heat capacity of 4.184 joules per degree Celsius at 25 degrees Celsius. What's the minimum volume of water necessary to contain the heat without boiling the water? And just a note here, 1 gram of water is equal to 1 ml of water. Go ahead and pause the video and try and figure this out, and then we can go over it. All right, well, we always start with this relationship that the heat of one thing is equal to the heat or the negative heat of the other thing. In other words, the heat gained by our water is equal to the heat lost by our iron. We can then set up our mc delta T equations for each of these. And in this case, we're looking for the minimum volume of water, and we notice the volume and mass are related. So we can just solve here for the mass of water. So we'll just divide over the C delta T for water into here. And at this point, it's really just plugging in numbers, right? We've got our two heat capacities. We've got a heat capacity for iron, one for water. We do want to convert our mass of our hot iron from kilograms to grams. Why do we want to do that? Well, because our heat capacity is listed in grams, not in kilograms. So we'll convert that. We've also kind of got to figure out what our delta T is here, right? So one is starting at 25 degrees, the other starting at 200. We know those are going to move towards each other, but where are they going to stop? Well, the question says, what is the minimum volume of water necessary to contain the heat without boiling the water? So this is the minimum amount of water we'd need to avoid boiling. So if you remember, the boiling temperature of water is 100 degrees Celsius. So if we heat the water right up to 100 degrees Celsius and stop and don't add our delta H of vaporization in terms of energy, the water won't boil. So our delta T of our iron, it's going to have a final temperature of 100 degrees Celsius and an initial of 200 degrees Celsius. So it'll actually have a negative 100 delta T right here. And then for the water, it's going from 25 degrees to 100. So that's delta T will be 75 degrees. Now you'll notice right here we have a negative delta T, but luckily we've also got this negative sign right there that'll cancel out and get us a positive mass of our water. So our mass, if we plug all this into a calculator, it's going to be 143 grams. And we noted that 1 gram of water is equal to 1 mil of water. So that's equal to about 143 mils. Of course, we only started with 1.0 kilograms, so we're only getting 2 sig figs here. So the answer is going to be B, 140 mils. Okay, let's get into calorimetry a little more seriously now. Let's look at how this is done. Well, we want to heat up an object, right? So one way we could do that is we could just put the object in a flame, see if it comes out at the right temperature. We could try and make sure that the object is fully heated evenly across it, but that's kind of hard to do if you're just putting it in a flame, or if you put food in an oven, for example, the outside of your food heats up first and the inside heats up later. So it can be kind of difficult to come up with an exact temperature unless you come up with a really clever system where you know the temperature really well and the temperature is set at something that it can't vary from. So one way of doing that is by putting material actually in boiling water. The reason that we do this is, right, boiling water, if it's boiling, it's always at its boiling temperature. And we can measure its boiling temperature super easy. You just stick a thermometer in there, right? So even if we're in Provo, we can do this really well, and we can figure out our temperature of our boiling water. We let our material, whatever it is, let's say we're trying to measure the heat capacity of sodium chloride, put a bunch of sodium chloride in a test tube here, and then just watch or just wait for a while until the heat inside the sodium chloride is equilibrated with that outside. We can then take a closed container of water, a closed container with a known amount of water and a known temperature of water, and then we can add our material in at the bottom here. If it's something that'll react with water, we can have it in a container or something like that. And then we'll just measure how much the water changes temperature, right? And we use this same relationship, that the negative heat of our substance is equal to the heat of our water. In other words, the heat lost by our substance is equal to the heat gained by our water. And we turn back to our old familiar MC delta T equation, right? But there is a little bit of a problem with doing this. So this is how calorimetry was done historically, and in some cases it's still done this way fairly often. But the problem is that you lose some heat if you take your material from here and you put it in your container, right? You're also opening the lid. There's some chance of spilling your solution. There's some chance that you didn't measure the mass exactly right. There's limits in thermometer measurements, etc. So there's a lot of places to introduce error here. So a better setup is actually to start by heating this thing inside your calorimeter to start with, inside what we call a sealed container or a bomb. So you'll hear the word bomb calorimetry going forward here, and this is what a bomb calorimeter looks like. So it's got a little container where you're going to carry out your reaction, and that container is usually surrounded by water, encased in some sort of insulating container. It's going to have a thermometer sticking in there to measure the reaction, and it's going to have some sort of stir so that the water can interact with this container and equilibrate temperature really fast, right? Because the thing that's going to heat up most quickly is the water that's right around the container. So if you've got this mixing, then the water that's around this container is constantly changed for other water. Then if we're trying to measure, for example, the energy content of food, we put some food in here inside this sealed container, and then we would combust that food and see what happens. So if that food is burning, then it's going to heat our calorimeter, right? And so in this case, our reaction heat is going to be absorbed by our calorimeter. And the calorimeter, the heat that's absorbed by it, we could figure out exactly how much water is in there, figure out the exact composition of this bomb container, of the insulator, how much energy will be absorbed by the thermometer, how much will be absorbed by the stirrer. There's actually a lot of parts here, all of which can store heat. So instead of doing that and figuring everything out, let's just figure out one heat capacity for the whole system, right? We can do that just by running a reaction that gives off a known amount of heat. then we can just see if that known amount of heat gives off some amount and our calorimeter changes by some temperature, then we know what the overall heat capacity of our bomb calorimeter is. And then we can run a second reaction for whatever we're interested in, figure out what that reaction's heat is. All right, so let's try this. Let's try and figure out the heat capacity of a calorimeter if burning 1 gram of benzoic acid increases the temperature of our calorimeter by 7.248 degrees Celsius. And by the way, the combustion of benzoic acid releases 26.38 kilojoules per gram. Well, then we just set up this equation. The Q of our reaction is equal to our Q of our calorimeter, and our Q of our calorimeter is just equal to the total heat capacity of our calorimeter times our change in temperature. So here we're looking for C, so we can just solve this thing for C, and now we have C equaling negative Q over delta T. Now, what is our actual Q of our reaction? This can be a little strange. The reason I say this is because you'll notice there's a negative value here in front of our Q delta T. So if our Q is positive and our delta T is positive, we'd have a negative heat capacity for our calorimeter. That's not really allowed. So either our Q has to be positive and our delta T would have to be negative, or our Q would be negative and our delta T would be positive. That way, this ratio gives us a negative value, and a negative value times this negative value would give us a positive heat capacity. So our system that we're looking at for the Q of the reaction is the reaction itself. So this is going to be the heat given off by that specific reaction. So the heat, it's going to be the heat change for the reaction. And that reaction, since it's giving heat off to the environment, is going to lose heat itself. So we're going to have to put a negative sign in front of there. So this is going to, the reaction is going to lose negative 26.38 kilojoules for every gram that's burned. And then those negative signs can cancel out. So we plug these guys in, we do our math, and we find that the calorimeter has a heat capacity of about 3.64 kilojoules per degree Celsius. All right, let me let you try this. Let's say the combustion of a standard releases 100 kilojoules of heat and raises the temperature of the calorimeter by 14.8 degrees Celsius. What is the heat capacity of my calorimeter? Go ahead and pause the video and try and figure this out. All right, we're going to just use this same equation again, right? That the negative heat of our reaction is equal to the heat of our calorimeter, and our heat of our calorimeter is equal to the heat capacity of our calorimeter times our change in temperature. Again, we'll solve this for our heat capacity of our calorimeter. That'll just be equal to negative Q of our reaction divided by our change in temperature. So again, the combustion of this standard is releasing 100 kilojoules of energy. It's releasing it into my surroundings, meaning my system is losing 100 kilojoules. So my Q of my reaction is going to be negative 100 kilojoules. So I can just do 100 divided by 14.8. The negative signs will cancel out, and I'll get an answer of 6.76 kilojoules per degree Celsius. All right, now let's keep going with this. Let's just keep practicing these calorimetry problems. Let's say the heat capacity of some calorimeter is 7.794 kilojoules per degree Celsius. Let's say the temperature of the calorimeter increases from 25 degrees to 39.5 degrees when a handful of peanuts are burned in it. How much heat in kilojoules is generated? And then I also want us to figure out how many in calories. Well, the heat absorbed by our calorimeter is just equal to the heat capacity of our calorimeter times our change in temperature, right? So in this case, all we have to do is subtract these two temperatures from each other and multiply by our heat capacity. So that'd just be 7.794 kilojoules per degree Celsius times 14.50 degrees Celsius, right? That's 39.5 minus 25. And that'll give us a heat value of 113 kilojoules. So however many peanuts were set in there, that's how much energy they gave off when we burned them. Now this question also wants this value in calories, which is logical since we're using a calorimeter. So for that, we're just going to take 113 kilojoules times by the ratio between calories and joules, which is 1 calorie for every 4.184 joules. And that'll get us 27.01 kilocalories, or 27.01 uppercase calories or food calories. You'll notice here I went from kilojoules to kilocalories by using the ratio between calories and joules. So it turns out if you're going to be in the same frame, so here I'm going from kilo to kilo, then I actually don't have to convert my conversion factor to that same value. I could pretty easily, right? If 1 calorie is equal to 4.184 joules, then 1 kilocalorie is equal to 4.184 kilojoules. But you can also take this little shortcut and not put the K's in there as well if you want. All right, let's keep going and introduce you to a new topic that we'll explore pretty heavily in the next 2 lectures, but that's our delta H of our reaction. In general, we think of our delta H as the heat either given off or absorbed during a chemical reaction. And some chemical reactions do end up absorbing energy from their surroundings. These would be endothermic reactions. We have exothermic that give off heat and endothermic that are absorbing. Well, let's say that 1 mole of methane is combusted with excess oxygen in a constant pressure calorimeter, like the one we got here, with a heat capacity of 7.794 kilojoules per degree Celsius. The temperature of the calorimeter changes by 102.9 degrees Celsius. So this is a big change in temperature, right? 102 degrees is a big change. What is the change in enthalpy per mole of the combustion of methane? Okay, in this case, we're still doing this equation. Our negative Q of our reaction, whatever's getting combusted in here, is still just going to be equal to the heat of our calorimeter. But in this case, we're going to change our Q reaction into what we call our delta H of our reaction. Your delta H of your reaction, your change in enthalpy, is equal to the heat of the reaction when you're using 1 mole. These delta H values are always for a single mole of whatever reaction you're looking at. And so this is a way of quantifying the energy that's released from 1 mole of a reaction. All right, so we have that. We know that delta H is equal to Q of our reaction, and we know that Q of our calorimeter is equal to the C of our calorimeter times our delta T. And now we can just plug in numbers. So we've got our heat capacity of 7.794, and we've got our change in temperature of 102.9. You'll notice I moved the negative sign from here over to here when I'm plugging this in so that I can solve for the actual delta H of my reaction, the actual heat released. So you'll notice that the delta H of my reaction is equal to negative 802 kilojoules. So if my delta H is a negative value, how did I increase my temperature? Remember that this delta H is actually referring to the system, or it's looking at this heat in terms of what's happening in the system. The system gave up 802 kilojoules of energy to the surroundings, which means the energy inside the system dropped by 802 kilojoules. So anytime you have a delta H that's negative, that means you have an exothermic process. If you have a delta H that's positive, then you have an endothermic process. Now what is my delta H for combustion then of 2 moles? Well, what is my heat change? Well, I just figured out my molar enthalpy for this reaction. It was negative 802, so I just take 2 times negative 802 and get negative 1,604 kilojoules for 2 moles of reaction. And it's just that simple. Let me let you try this now. I'm going to have 1 mole of butane. It's combusted with excess oxygen in a constant pressure calorimeter. I've got my heat capacity of my calorimeter here. The temperature of the calorimeter changes by 144 degrees Celsius. What is the change in enthalpy per mole of the combustion of butane? Go ahead and pause the video here, try and figure this out. All right, again, we're just going to use this equation, our negative Q of our reaction being equal to the Q of our calorimeter. Our Q of our reaction is equal to this delta H value, our change in enthalpy per mole. And our Q of our calorimeter is just equal to the C delta T of our calorimeter. So we get this equation again, and then we can just plug in our heat capacity of our calorimeter, which is 20, and our delta T, which is 144, Make sure to move the negative sign off of the delta H so that it's on the C delta T here. And our delta H of our reaction is going to be negative 2,880 kilojoules. But we're only starting with 1 mole of this, and our heat capacity is only listed to 2 significant figures, and so our answer can only have 2 significant figures as well. All right, now you might not have noticed it, but we actually talked about 2 types of calorimeters. We talked about this open calorimeter, right? One where the lid is not on this. So this is what we call a constant pressure calorimeter. Because if I put something in here, then pressure, if I change the pressure, it's free to escape out the top. This type of calorimeter is really useful for a heat capacity measurement, but it's not good for anything that undergoes a phase transition or causes any kind of real reaction to happen. Because real reactions are going to usually cause bubbles or other things that would cause you to lose some of your mass of your water here. So these constant pressure calorimeters, really good for heat capacity. And just to review how we use these, we put a known amount of hot sample in our calorimeter, we use a known amount of water, and we measure our change in temperature of our water here, and that'll give us our heat capacity of our unknown material. Because we know the mass of our water, we know our heat capacity of our water, and we measure the delta T. For a constant volume calorimeter, this is what we call a bomb calorimeter. We have this setup, right, where we have this closed container, we put a lid on this. And this is really good for determining the delta H of reactions. If you try and explode something in a constant pressure calorimeter, it's going to explode all your water out. You just screwed everything up. So you pretty much have to do delta H's of reactions in a bomb calorimeter. In this case, we're going to blow up a known amount of material in here. And often this is going to be food, so it'll be combustion, but you can do other reactions in here too. So for example, you can have sodium metal reacting with water, or you can have any other number of non-combustible experiments occur, and that will give its heat off to the surrounding water. So we'll measure the heat absorbed by the calorimeter, so we'll measure the temperature change, and we'll measure the heat capacity of this calorimeter previously, and we'll use that change in heat to calculate our delta H of our reaction. We'll get really deep into delta H's of reaction next time, but if you have any questions for the time being, feel free to let me know.